Okay, so now we're going to talk, there's a brief section on model selection, so to kind of get a preview of that. So we'll just go over this section, and I thought because it's such a short section, at the end I'll go through some of my own work where I've used model selection to kind of give you a sense of some of the options that are possible and my own experiences with them. So first we'll kind of read through the section, and then we'll switch gears a bit, and I'll show you a couple of examples of kind of model selection in some real-world applications. Okay, so I've pasted this example. Let me switch to the this example that we have that we're using throughout the chapter of the curve fitting, and you'll remember that when we were using the error functions to kind of measure the goodness of fit, the least squares error, we had a range of model complexities that we could try. So those were like, are you going to model your data here? Are you going to model it with a linear fit, a constant fit, a parabola maybe, something more complicated. So there was this notion of the model complexity, and as far as the linear fit, as far as the least squares error was concerned, you just gave it, okay, like we're going to use a ninth order polynomial. But the question is, how do you pick the order of that polynomial? And the issue is not doing well on the training set. The issue is basically being able to give the best predictive performance on data you haven't seen. So we saw that, for example, in this particular case, a ninth order polynomial can go through all your data points exactly. But if you give it a new example that it hasn't seen, it's very unlikely to be able to capture the new data point. So the idea is, how do you select the model complexity? How do you pick the model complexity in a way that gives you the best predictive performance? Okay, so that's kind of what we're going to be talking about here. All right, yeah, so as we just discussed, when we do the maximum likelihood approach like we were doing with the least square setting, you shouldn't use the training performance, because the more complex your model is, the better it'll do on training data. It just has more knobs to turn, so it will fit your data better. And so and that phenomenon is called overfitting. So having essentially taking, for either having a model that's too complex or is rich enough that it can capture your training data very well in such a way that that's not indicative of its performance on held out data. So you have to just worry about that. So one way to kind of a straightforward way of evaluating your actual model's predictive performance is you hold out a chunk of your data, called it into what's called a validation set. You train on the remaining bit, and then you test your performance on that validation set. So that's what this is about. And that can work. The only thing is, sometimes you have like lots of parameters to test. So if you're, if you're using the same validation set all the time, then you can start overfitting to that, right? So like, let's say you find that, okay, so a parameter 4 model is, is really good on the validation set. Maybe you have some other parameters to test, and you'll start kind of tweaking them to do really well on that validation set. Then all of a sudden you're kind of at the risk of overfitting again. So the idea is, well, what you can do is you can leave out a further kind of test set to then say, evaluate the performance after you've done all of your tweaks. So maybe you can use the validation set to kind of pick the best parameter and then report the performance on the test set. And you will see that, and actually one of my examples, I'll show you what that looks like. Okay, so now what will happen is that, okay, so this is great if, let's say, you're fitting a 3-parameter model and you have your hundreds of thousands of data points. So you just put some of them aside for test and some for validation. But often you don't have an infinite amount of data. So if you just use one validation set, you'll get a very noisy estimate of your predictive performance. So the idea is to what's called cross-validation. And so what you can do, so I'm call it K-fold, or in this case kind of S-fold cross-validation, is you split your data into chunks, into like S different chunks, and you use all but one of them to train your data, and then you test on the remaining. So that's called K-fold, or in this case S-fold cross-validation. So here's kind of an example of how that would work. So here is your data. In the first run, you will hold out this little bit as your test or your validation set, train on this set, and then evaluate on that. And you just keep doing that for multiple runs, and it gives you kind of a sense, and you average your performance on the held out data in each of these cases to give you a sense of what your performance would be, a less noisy estimate of what your performance would be on held out data. So that's one way of doing it. And a special case of that is if you hold out all but one of the parameters. So let's say you have your hundreds of thousands of data points. So you just put some of them aside for test and some for validation. But all of a sudden you're kind of at the risk of overfitting again. So the idea is, well, what you can do is you can leave out a further kind of test set to then say, if you all but one of your data points. So if you split your data points, your data into n groups, where n is the number of data points that you have, well then you've got what's called we'll leave one out cross-validation. So you just left one data point out, you test on it, and you train on the rest. And one thing I want to point out is that so back when I was in grad school, I had to kind of write all the code to do these things myself, to do all the cross-validation myself. But these days, packages like scikit-learn, they have all of this stuff built in for you. So you can go in there and you can just use classes that, for example, do the k-fold cross-validation we're talking about, or various variants on that. So this is not, it's very easy to do this now these days, to run cross-validation, to evaluate models. So then all you have to worry about is, picking a good model for your data. So a lot of the complexity has been removed out of this. Now you can imagine that, if you're going to do cross-validation, so let's say you're going to do S folds, even S is 5 or 6, and you have lots of parameters to test, and you want to test all the different combinations, you're going to end up getting in a situation where you're exponential in the number of parameters, because you want to test every single combination, and that's going to take a very long time. So one possibility is that you want to kind of, is it possible to use a situation where we can evaluate our models just using the training data, but without suffering the bias from overfitting? So is it possible to avoid having to do cross-validation, but just use your entire training set, so you get the additional benefit of using your whole training set, but without overfitting? And so people have come up with mechanisms for doing that, and these are kind of these information criteria, which you might have come across and I've come across as well. So for example, there's the AIC information criterion, AIC, you might have heard of, and what that does is you take the log likelihood of your parameters. So here's you find your maximum likelihood estimate, and you get the log likelihood of your data, of your parameters actually, and then you subtract a term for the order of your model. So in this case, that would be m. There is another one called the Bayesian information criterion, which is kind of similar, and I think we'll be talking about it later on. One issue that Bishop raises about this is that they don't take into account the uncertainty in the model parameters. So for example, we just have the maximum likelihood estimate, whereas we just saw in the previous section that the proper Bayesian way of doing things is to actually integrate over your uncertainty in the model parameters. So these are maybe kind of stepping stones to that, or maybe good useful heuristics to use if you don't want to do the full Bayesian thing. But there is a proper Bayesian approach to doing this, and I think the right approach to take is not to start with the approximations, but to try to do the Bayesian approach. And if it's too complicated, or if it's too the integrals are too complex, too numerically difficult, then you can make principled approximations to those, rather than starting with an approximation right off the bat. In my experience, so I have used some of these in the past, in my experience I find that they work okay, but you still have to tweak, how do you measure the parameters, or kind of the contribution of the parameters in this penalty, and so there's still kind of some tweaking you have to do. And so I've ended up either doing the cross-validation, which I'll show you, or I've ended up just doing kind of a Bayesian, the Bayesian approach, but with an approximation to make the integrals tractable. But it's good to know that these things are out there, and you will see them. And for example, scikit-learn will allow you to compute them as well. So it's good, and I think it's worth trying on the models you come across. Okay, so I think that's basically this section. So I thought I'd give you a couple of examples of how I've used model selection on real-world problems, so kind of through my own research. So let's have a look at that, and I'll tell you what I was working on to kind of give you some context, and then where model selection came up, and just a brief preview of how I approached it. So let's switch gears here. So I'm going to switch to there we go. Okay, excellent. So this is from a paper, and I'll put the link to the paper in the description of the video. So this is a paper that I was on from about 10 years ago, where one of my lab mates had gathered this really nice data set of the responses in the olfactory system of the locust, so the sense of smell of the locust, to various odors and odor mixtures. And in this particular data that we're looking at, we're trying to see what happens when you morph one of the odors from one component to the other. So there's like citral, which is one component of an odor, and I forget, it smells kind of lemony. I don't know what octanol smells like, but you kind of morph the odor. So you start at just 100% citral, and then you start mixing in more octanol and taking out citral until until it's fully octanol. And what you do during that morph is you look at the population response, and that population response, we had, my colleague Kai, he gathered about 100 different neural responses. So we can't look at that in the full 100-dimensional space. So we did some. So he did some dimensionality reduction to look at that population response in a reduced space. And what you can see, yeah, you can see my mouse, terrific. So the idea is here's the odor morph. So this is kind of the population response to each of these odors. So you can see, let's say when we just did purely citral, when the odor would come on, the population response would kind of go out onto this wing and then come back down and then come back to the starting point. And then as you morph the odor from one to the other, well, it starts kind of shifting until at the very end, it's kind of doing a loop in another corner of that space. And now there's kind of a debate in the field about is this flipping that's kind of happening from one end to the other, is this happening smoothly, or is this happening in a stepwise manner? So people were arguing that, well, based on various properties of olfactory neurons and what we know about the system, that actually things are happening in a stepwise manner. That maybe actually, it hangs out a little bit on the citral side, on this green side, and then it switches to the red side. And so this was kind of just and we can't really tell from these pictures. So what I did, one of the things I did on the paper was to try to kind of quantify these statements and try to say, well, how could we tell whether it was happening in a stepwise manner or it was happening in a kind of a linear manner? So the way we did that was by essentially building a few different models to fit the data and then doing model selection. So let me show you what that would look like. So if we switch gears. Okay, excellent. So what we did here was, what am I showing you? So here on the x-axis is a measure of how strong, essentially where you are in the mixture. So when you are all the way over here, that's a fully octanol mixture, and then when you go on this end, that's a fully citral mixture. So you're kind of doing the morph as you go along. And this is kind of at various data points. So at -1, the odor hasn't come on yet, and then at time point 2, the odor's come on. I forget how long the odor was on for. So I think it's on for the rest of the time here. So we're taking little snapshots. Now, what's on the y-axis? So the y-axis is what's called the correlation distance. So what we do is we take the whole population response at that particular time point of the 100 neurons, and we correlate them with the response for pure octanol. So the correlation distance would be 0 for an octanol response, and then it would increase to some value, some large value, as you get more towards citral. So we're essentially measuring distances, the distances of the population representations of different mixtures of odors. So here, this particular point here is mostly octanol, not perfectly octanol, but mostly octanol, all the way to nearly all citral. So we're trying to see, how are these distances changing as we morph the mixtures? And the hypothesis being that if it's stepwise, well, then you would expect that maybe the distances would kind of stay at whatever value until there would be some kind of a threshold procedure where situation where all of a sudden they would kind of shift in a stepwise manner and go to some new value. So, and if it was a linear, if it was more smooth, then maybe they would just kind of gradually shift. So what we did was we essentially just tested these models. So we had a few models that we considered. There was the constant model. They've actually got them listed up here. Maybe you can't quite see it there, but I can shift it down. So here we go. So there was a linear model, a constant model, a one-step model, and a two-step model. So let's have a look at how they do. And so here what I've just shown is, if I move this over a little bit, let's see. Yeah, okay, I'll just stick with this. That's fine. Okay, so yeah, you can see that very well. Okay, so the idea is that in each one of these panels, I'm showing the performance of the best fitting model after the model selection, so accounting for the complexity of each model, and the second best in gray. And what we saw was, and when you do this model selection procedure, the Bayesian model selection, which is what I did here, it accounts for the additional complexity that more sophisticated models produce. So essentially it says that if you have a fancier model that has more parameters, it has to be able to explain more of the data. So what it showed was that when, before the order had come on, although the best model, the second best model is the linear model, it's actually, the data is actually, when you account for the complexity that the linear model brings, it's actually best explained by a constant model that doesn't even have the additional complexity of the slope that the linear model introduces. So it says that, before the order comes on, there is actually no effect with concentration. And that, that's going to be in agreement with our intuition. Now then, as the order does turn on, you can see that actually the second best model in each case in gray is kind of a stepwise model. And so, and I'm showing it for its the best parameters, because we actually integrate out all the model parameters when we're looking at them. But it turns out that despite the fact that the step model can can fit the data quite well, actually the linear model, which is a little bit simpler, actually describes the data better when you account for the complexity of the model. And I think in another step, we even had kind of a two-step model was being considered as well. And even though those were the second best models, the best model that fit the data when you account for the complexity of the model was the linear one. So and with that we could conclude, well, as far as our data shows, the transitions are actually smooth. And what's great about this is A, we can make a statement like that, but then B, somebody can come and say, well, actually, I disagree with you because, for example, I think the stepwise model wasn't the right one to use. Here is a better one that you could use and you could test. And then that's something that we can go and actually test concretely and then have kind of a concrete discussion about that, rather than, well, I don't know. I mean, is linear the right thing to use? I mean, you can plug all these things in, at least try to think about what the optimal, the proper way of comparing the models would be. And then if those are too complicated, you can then make approximations, and every one of those steps you can actually kind of discuss and debate. And there's, you remove as much as possible any ad hoc steps. Okay, and how did we actually do the model selection in this particular case? Well, let me show you. So this is, and we'll see this in future chapters, I expect. But essentially the idea there is you just compare the posterior, just like you would expect. You compare the posterior probability of one model given the data to that of the other model. And so then you just kind of apply Bayes' rule. So you get these terms. And now the most important, what you end up with is something like this, where you have a prior on the model multiplied by the probability of that data given the model integrating over the parameters of a model. So you can imagine that, and here is kind of what it comes down to. So again, you have the prior on the model, and now the probability of data given the parameters, and then the probability of the parameters for a given model. So this is all just kind of Bayes' rule being applied here. And the idea is that more complicated models, although they'll be able to fit the data better, there will be more parameters. There's the probability is spread over a kind of a larger parameter space. So they won't necessarily, this result, just because you have a more complicated model, doesn't mean that the corresponding numerator will always be the simpler model. Sometimes the simpler models can actually end up explaining the data, given the complexity, they can explain the data better because they don't spread their probability mass over such a large parameter space. So this is kind of how this is one way you would do the model selection. You would just do this, you would compare the posterior probabilities of the models given the data. So again, going from a prior and then having a likelihood term of the model given the data you've seen. And then that comes down to evaluating these integrals over the parameters. And in my case, those integrals weren't super easy to evaluate. So then I said, okay, I'm going to approximate those integrals using something called Laplace's approximation, which we'll discuss later on in the book. But the point was that we went and we had a principled. You could use the Bayesian approach. You have a principled answer to the question, and then if parts of it get too complicated to answer in that approach, you can then make hopefully principled approximations to come to a reasonable conclusion. Okay, so that was kind of the Bayesian approach to doing one application of the Bayesian approach to doing model selection. The other one I wanted to discuss is kind of something that I'm doing now, where essentially we're using cross-validation. So let me switch to PowerPoint. So here's another project where we're looking at the input-output transformation of an olfactory structure called the olfactory bulb. So it sort of doesn't matter too much what these things are, but essentially this is some input pattern of covariance. This is an output pattern of covariance, and we're trying to build a model that can transform this input to the output. So we do that. We have some model that has neurons interacting with some connectivity W, and now we're trying to learn, we use different models for that connectivity in an attempt to try to predict, to fit the data that we see. So here's kind of an example of that. So again, here's the input, the output, and then the output of one of the models. So this is a kind of a free symmetric model, whatever it is, and how we, some measure of how we quantify it. So to kind of give us a better sense of, what connectivity works, we actually also test various models of connectivity. So instead of saying, well, every neuron can be connected to every other neuron in an arbitrary way, which is a free situation, and that's one where we have, again, lots of parameters. And so there'll be kind of potential for overfitting, but so we have to regularize quite heavily. On the other end, we have models that are where they say there's actually a neuron is only connected to itself. So there are no lateral interactions, and a bunch of models in between. And we just want to see, okay, well, how well do these different models of connectivity do? And so this is now this is kind of another way of doing model selection where we use cross-validation. So for example, that diagonal model, it has this one regularization parameter lambda, which hopefully you can see down here. And now we have a training set, a test set, and a validation set. And when the regularization is low, the model fits the data very well. So this ratio low means a good fit. As the regularization increases, the models essentially stop being able to actually fit the data because the penalty is so high that the models basically can't do anything. So they end up performing poorly. But there is kind of a sweet spot in the middle here where the test set and the validation, the test error and the validation error have actually come down a bit. So the test and validation error will start out being high because at very low regularization, because you're essentially overfitting. But as you raise the parameter, the regularization parameter, there will be kind of a sweet spot where actually the validation error will drop, and then you can use that to get your model parameters, and then you can evaluate your performance on a test set. So that's effectively what we do. So I think I use the terminology in reverse, but essentially what we do is we find the value of lambda at which the test set has the lowest ratio, so the best performance, and then we report the performance of the model on the validation set. So we use one data set to get the model parameters, and then we want to say, well, which model is best? So we report the performance on data that we haven't seen in the validation set. So if we do that, now we get a range of different performances for the various models we're looking at. And surprisingly, this diagonal model, despite it being so simple, actually is quite competitive with the best models there. And again, so we have these regularization parameters at the bottom, and we use them to prevent our models from overfitting. And to do that, we've used a cross-validation procedure where we've repeatedly held out some of the data to find the parameters with, and then held out an additional bit of the data to actually report performance on. So yeah, so I think that was about it. Let me switch back to the model selection chapter. So yeah, so I think I just wanted to kind of give you of course, go over this section on model selection, a really important topic. How do you pick the parameters of your model? And there was two methods discussed, which were using kind of cross-validation, and then these information criteria, and then also this the Bayesian approach. And then I wrapped up by showing you a couple of real-life examples of how I've used the Bayesian approach and also the cross-validation, which is mostly what I do now, to evaluate models and to also kind of pick parameters for the model. So this is all really important stuff. Really good to have a competent handle on it. And just I also want to emphasize that so these days it's very easy to learn about these model selection and to actually perform model selection. So scikit-learn has really excellent tools and classes and functions for doing just that. So you shouldn't have to write any of your own code. You can just use their code, and they also have really good documentation, so you can learn all about it. Pitfalls, approaches to using the various options. So I would highly recommend that. I'll put a link to that in the description as well. So I think that was about it for this session, and next time we'll talk about the curse of dimensionality. Thanks.